you can tell the difference between whether it was the index finger or the middle finger that was probed. Well, the reason is because these two cells send their axons to different locations. And so if we think about the skin as being a topographic input space, just meaning that there's a mapping between a representation in your brain of that skin and a set of neurons that kind of encodes for different locations on that skin. Well, in that sort of framing, which I know is a bit obtuse, and hopefully will become more useful as we move forward, and you think about the concept of receptive fields, not just as it relates to your fingers or not just as it relates to the retina, but to kind of higher order concepts as well. But if you think about the skin as being the input space, the difference between whether this neuron is active or this neuron is active is based on where on this input space there is a physical input being put in. So when we put a probe that depresses the skin on the index finger, that location in this sensory input space has been mapped to this specific neuron because the axon of that neuron runs specifically to the location that we're probing. When we're talking about vision, the input space is not defined by the sheet of skin covering your body, but rather by location on the sheet of photosensitive neurons that we call the retina sitting on the back of your eye. We can talk about this input space based on coordinates that are defined based on where a pattern of projected light falls on the retina, and we can talk about the topography of the input space as being defined in retinotopic coordinates. And all that means is where on the retina does a particular pattern of light projected from the front of the eye. All that means is describing a dot of light or a pattern of light that's being projected from the eye onto the retina, describing where that dot of light or that pattern of light falls in coordinates that are defined relative to the position on the retina. So let's look at this diagram or this example from the book. So the idea is that we have two retinal ganglion cells, and we assume that we can record using recording electrodes the activity, the electrophysiological activity of the retinal ganglion cells that are located at the two locations marked as A and B on this drawing. So if we assume that the light beam that's being shown in this drawing, it turns on and then off with the profile shown here, what do we expect the response of a retinal ganglion cell at location A to look like? Well, let's just assume that this retinal ganglion cell fires when it's in the light. As we'll see, this assumption might not be exactly correct, but let's just assume that it does. If that's the case, then what we expect to see is that when the light turns on, we start seeing action potentials at location A, at a retinal ganglion cell located at location A. And I've drawn action potentials as a bunch of tick marks on this plot. Now, what do we expect to see at location B? We don't expect to see anything at location B, right? Shining a light on location A is not going to cause the cell located at location B to fire. And the reason for this is because the light that's shining on position A does nothing to excite photoreceptors that are located in position B on the retina. So getting back to this concept that the receptive field of a particular neuron is the area in input space that causes that neuron to be active, the receptive field for a particular retinal ganglion cell is the location on the retina where if you shine a beam of light, the cell becomes active. Or maybe to be a bit more precise is to say the location in these retinotopic coordinates where a pattern of light will modulate the firing of the retinal ganglion cell. So in this example, the receptive field of a cell located at position A is some area located here. So that is the input space that causes a cell at location A to fire, whereas a cell at location B has a receptive field that is somewhere down in this location. So now let's apply the same concept to a particular cone and say, what is the receptive field of this cone? The receptive field of the cone would simply be the location described by its circumference, because that would be the area where any incident photon that entered the retina would strike one of the opsin molecules located inside that cone and be able to modulate the activity level of that cone. A photon that fell outside of this region would not be able to modulate the activity of that cone because it wouldn't hit any of the disks and therefore wouldn't interact with an opsin molecule that would be able to influence the activity of that cone. So now let's extend this concept to a bipolar cell, which is connected to the same cone that we were just looking at. And what's the receptive field of this bipolar cell? With the simple circuit that we've drawn, the location of the receptive field would be the exact same that we saw for the cone, because to modulate the activity of this bipolar cell, an incident photon would still have to fall on this part of the retina, so as to modulate the activity of the cone, which is synapsing onto the bipolar cell. So now what if we make the circuit a bit more complicated, such that there are 4 rods, all of which are synapsing onto a single bipolar cell? What's the receptive field of this bipolar cell now? Now the receptive field of the bipolar cell is the cumulative area of the receptive field of the 4 cones that are synapsing onto it. Since any one of these 4 rods is capable of modulating the activity of that bipolar cell, incident photons can fall here, or here, or here, or here, inside the receptive field of any individual rod making up this circuit, and still have the ability to influence the activity of this single bipolar cell. So we say that the receptive field of the bipolar cell itself is the cumulative space in retinotopic coordinates over which incident photons are capable of modulating the activity of this particular bipolar cell. So now, what is the receptive field of this bipolar cell? Well, the answer is becoming more complicated. And the reason the answer is becoming more complicated is because the way it's been drawn here, we see there's a population of rods that are feeding directly via monosynaptic connection into the bipolar cell. And so obviously, the receptive field would be something that describes the location, the cumulative location of those rods. But there's also a second class of photoreceptors that are disynaptically connected to the bipolar cell via this horizontal cell right here. And as a consequence of this more complicated circuit arrangement, we might expect that photons falling in this red region will be capable of modulating the activity of that bipolar cell as well. And so we need to define a receptive field that accounts for the fact that we have two different locations on the retina that can potentially influence the activity of this bipolar cell as we define the receptive field for this bipolar cell. Because of the more complicated circuit, we can't simply look at this and describe the receptive field of the bipolar cell without knowing more about what is it that this horizontal cell is actually doing with these inputs from the red region, and also knowing something about the bipolar cell itself. So is it an on or an off bipolar cell? What do I mean by an on or an off bipolar cell? Well, it turns out there are two different classes of bipolar cells that exist in the retina. One of them is called an on cell, and one of them is called an off. And we define this based on whether they are depolarized or hyperpolarized by the presence of light. So what I mean is that if we have two bipolar cells which are connected to rods, and we make recordings from these bipolar cells, while the photoreceptor that is synaptically coupled to those bipolar cells is being illuminated, we might see something that looks like this. If the light turns on for that period of time, V1 might look like this, and V2 might look like this, where in both cases, an increase in voltage would indicate movement towards the reversal potential for sodium, and a decrease in voltage would mean movement in the direction of the reversal potential for potassium. So V1, the cell on the left, becomes less polarized when a photon is absorbed by the rod that is connected to it, and the membrane potential of V2 becomes more polarized. So in this example, we would call V1 an example of an on bipolar cell, because light causes it to become depolarized, and depolarization, as we discussed in the previous content module, means that it will be releasing more glutamate from its own synaptic terminals, and so we say that it is activated or turned on by the presence of light. V2, by contrast, is an example of an off bipolar cell, because the presence of light causes it to hyperpolarize and thus release less glutamate, and so it is inactivated by the presence of light. Mechanistically, the reason for the difference between these two classes of bipolar cells is not because the rods are doing anything different. In both cases, the rods are responding to the presence of light, as we talked about previously, which is that the rods are releasing more glutamate in the dark and less glutamate in the light. But glutamate has an inhibitory effect on bipolar cells, which express metabotropic glutamate receptor type 6 receptors, and these receptors cause the cell to hyperpolarize or move towards the reversal potential of potassium in the presence of glutamate, which means in the dark, these on bipolar cells are hyperpolarized, but when light shines on the rod, that releases the mGluR6 mediated hyperpolarization, and the cell depolarizes as a consequence. Off bipolar cells, by contrast, express ionotropic sodium channels, both AMPA and kainate, that cause the cell to depolarize when the rod releases a lot of glutamate. When the light is turned on, that bipolar cell will hyperpolarize because there is less glutamate being released by the rod, and it will depolarize in the dark as glutamate release from the rod increases. To make this clear, let's assume that we have a circuit as shown here with a single rod, which is synapsing onto a single bipolar cell. We can record the membrane potential of the rod that we'll call VR. We can record the amount of glutamate that's being released at the synapse between the rod and the bipolar cell, and I'm going to call that. We can record the membrane potential of the bipolar cell, and we can record the amount of glutamate that's being released by that bipolar cell, and I'm going to call that IGLU2. And we couldn't, just so you know, we couldn't actually do this. This is a thought experiment. This is not something that you could actually do, at least not easily. So let's see how these two situations will differ. Well, let's assume that in both cases, for both types of bipolar cells, the light is going to turn on for a brief period of time. On our voltage plot, up is always going to mean towards the reversal potential of sodium, and down is always going to mean towards the reversal potential of potassium. So we expect that the rod, when it's in the dark, is going to be depolarized, and then hyperpolarized when the light turns on, and then go back to being depolarized. We expect the glutamate release to be high when the rod is depolarized, relatively low when it is hyperpolarized, and relatively high again when it is depolarized. Now here's where things get different, and this is because the on bipolar cell, remember, is hyperpolarized in the presence of glutamate by this mGluR6 receptor. So when there's a lot of glutamate, we expect it to be hyperpolarized. When the glutamate decreases, it depolarizes. When the glutamate increases again, it again hyperpolarizes. The off cell, by contrast, is depolarized via ionic currents through glutamate-gated AMPA and kainate receptors, such that it is depolarized when there's a high presence of glutamate, hyperpolarized when that presence goes away because the sodium conductance decreases, and then depolarized again when the glutamate increases again. As a consequence of these membrane voltages, the on bipolar cell will release relatively low levels of glutamate when it is in the dark. That release will increase when it is in the light, and decrease again when the light turns off. The off bipolar cell will have an opposite glutamate release dynamics because of the difference in the off bipolar cell membrane potential. Now we have the basic framework to talk about what these receptive fields are, but let's see an example of what receptive fields actually look like by watching recordings from the original experiments performed by David Hubel and Torsten Wiesel recording receptive fields in a cat. In these experiments, a cat was anesthetized and placed in front of a screen on which the experimenters could shine patterns of light. These patterns might be an annulus, a solid dot, a bar, or anything similar to this, and the experimenters would rotate and translate these different visual stimulus patterns across the screen so as to project patterns of known geometry onto the cat's retina. And while they were doing this, they were recording action potentials from cells in a location of the brain called the lateral geniculate nucleus, and we'll talk more about the LGN next lecture. But it turns out that the receptive fields of cells in the LGN have the same basic geometry as retinal ganglion cells, and so I'm going to show you the results of these experiments because it will illustrate the light patterns that activate ganglion cells. As this video plays, you'll hear a crackling sound, and that crackling sound is the electrical waveform generated by an action potential being played through an audio amplifier. So when you hear clicks or crackling. That means the cell that is being recorded from is firing action potentials at a high frequency. This diagram summarizes the results of these experiments, or the conclusions from these experiments, which is the discovery that retinal ganglion cells have what we call a center-surround receptive field organization. In this diagram, they're showing the response of an off-center ganglion cell, and what they found is that the production of action potentials, when the area of the retina defining the receptive field is fully illuminated with light, the retinal ganglion cell fires action potentials at a low rate. When a dark spot is projected onto the very center of this location, but the surrounding area is still illuminated, we see the retinal ganglion cell firing with a high rate of action potentials. And when the size of this dot is extended over the entire location of the retinal ganglion cell's receptive field, we see it firing at an elevated rate relative to A, but at a lower frequency than in B. And what we now know is that this complicated geometric arrangement, where stimulus in one central area excites the cell maximally when the opposite stimulus is presented in a region surrounding that central region, is caused by the activity of horizontal cells that define a surround region which inhibits the response of the central region. Retinal ganglion cells with these off-center receptive fields will tend to show a low level of activity when the entire patch of retina above the retinal ganglion cell is illuminated, and this spontaneous activity will decrease as a dark line is projected onto some component of the receptive field's surround. The firing rate will increase as the shadow moves over so as to cover the central region, and will somewhat decrease when the entire receptive field is covered in shadow. In fact, the stimulus which will generate the highest frequency action potentials for this retinal ganglion cell would be a region of shadow projected directly onto the center with bright illumination covering the entire surround. And the greater the difference between the intensity of the light in the surround relative to the darkness in the center, the greater the firing rate of the cell. For this reason, the receptive field of a retinal ganglion cell is not defined simply as a circle indicating the region on the retina where patterns of light can modulate the firing of the retinal ganglion cell, but rather by indicating the locations where luminance and shadow combine so as to generate the maximal response of the cell. The figure that I've drawn here would describe an off-center retinal ganglion cell receptive field and indicates that the cell is maximally activated when the central region is in the dark, indicated by the minus signs, and the surrounding region is in the light, indicated by the plus signs. The diagram on the bottom shows the receptive field for an on-center retinal ganglion cell, which is activated by a bright spot of light surrounded by a ring of darkness. These receptive fields are created via the action of horizontal cells that inhibit signaling between photoreceptors located in the central region and the bipolar cell synapsing onto the retinal ganglion cell when the preferred stimulus from the center, and preferred stimulus means can be either dark or light depending on if you're talking about an off-center or an on-center retinal ganglion cell. So when the preferred stimulus from the center is extended into the surround, that stimulus via inhibitory activity of these horizontal cells inhibits the communication between photoreceptors in the center and the bipolar cell. But when the non-preferred stimulus is presented in the surround, this inhibition is diminished, allowing the preferred stimulus presented in the center to maximally excite the bipolar cell and thus the retinal ganglion cell. The geometry of the connections between the neurons in this circuit define a receptive field with inhibitory and excitatory regions shown here in one dimension, when extended to two dimensions, create the center-surround receptive field that we discussed previously. The diagram at the bottom of this figure is extending the example we discussed previously about how an off-center retinal ganglion cell would fire, so that we can consider what would happen if this retinal ganglion cell was translating across a large region of dark on the left and a large region of light on the right as the cell moves from a region of dark into a region of light. That is, as it translates across this boundary. We see a brief period of spiking followed by a period of quiescence based on where the edge of this dark light boundary falls across the receptive field itself, but that there is minimal difference in activity as the receptive field moves around within the uniformly dark or the uniformly light regions. Thinking about this from the perspective of the brain, listening to this retinal ganglion cell to try to understand visual space, this cell will maximally fire when an image containing a high contrast transition from dark to light is projected directly onto the location of the receptive field. The insight that the firing rate of this cell depends not so much on the actual level of illumination, but rather on the contrast between the central and surround regions of the receptive field explains the illusion that we saw several lectures ago, where we perceived two squares on a checkerboard to be different colors, even though the actual grayscale level was the same. The explanation is that even though these two gray regions are the same color, the retinal ganglion cell described by this receptive field will generate less action potentials at the transition crossing than a retinal ganglion cell described by this receptive field, because there's a higher contrast between the portion of receptive field in the dark on the bottom figure and the center of the receptive field than there is for the same region of the receptive field in the top figure. This difference in firing rates for receptive fields located along the transitions in these two figures explains why it is that we perceive this gray square to be darker than this gray square, even though in fact the gray is the same in both. This causes some interesting illusions, such as Chevreul's illusion, where we see scalloped edges where uniform gray bars meet each other. because the retinal ganglion cells along the edges are firing at higher rates on opposite edges of these transition zones, and can also create some rather startling illusions, such as in this demonstration of the Kafka ring, where our perception of a uniform gray circle changes dramatically when we change the relationship of that gray circle to the surrounding regions. And note that though we've been talking about this in terms of light and shadow for the rods, the same type of dynamic and the same type of receptive field organization also exists for retinal ganglion cells which are being fed by cone, except instead of simply being a question of the total luminance, there's also a degree of color opponency, such that P-type retinal ganglion cells signal contrast between red and green and blue and yellow regions projected onto the retina. This provides the starting basis for our ability to perceive color in the world around us. The antagonistic relationship between the center and the surround helps explain how it is that we were able to determine whether we're looking at something which is green or something which is red at intermediate wavelengths of light where both green and red cones respond with the same level of activity. This is a fun illusion illustrating the effect of color opponency on our perception of color, and what you're seeing is a rendering, a negative color rendering of the new computational science building that's being built on Commonwealth Avenue. And to see this illusion, what you need to do is pick a point in space. So fixate your eyes on that location in space for 15 or 20 seconds, and then hold your eyes on that location. When the image changes so as to remove all the colors, you should perceive the inverse of the colors that are shown in this image. As soon as you translate your eyes away from the fixation point, those colors should all vanish. So hold your eyes steady, and in 3, 2, 1, there. So if you did everything right, what you should have perceived is the image switching from the negative color to the normal color, so the tree should have looked green and the sky should look blue, but as soon as you moved your eyes, everything should have immediately gone to grayscale. You might think to yourself, this seems like a dumb way to organize the retina. Why would you do this? Well, the reason is because this actually provides our vision with some very nice properties. Total luminance, which is equal to the illumination, or how bright the light that is hitting something is, times the reflectance of that object. The information about a particular object, though, is contained not in the illumination component of this equation, but rather in the relative reflectance, because it's the relative reflectance that tells you something about the physical properties of the object itself. And so if you want to use vision to understand what is in the world around you based on the patterns of light that are being reflected off of them, the best practice or the best strategy is to figure out a way to delete this illumination and only report the reflectance. Another way of saying this is to discard the total luminance level and report only local contrast. And this is in part what the retina does. Retinal ganglion cells signal local contrast rather than absolute luminance. This is why we're able to see details of the world around us, whether they're illuminated by bright sunlight or in the shadows. Images described by the retina are much more like high dynamic range photographs, which capture contrast across a wide range of lighting conditions, than they are traditional photographs, which use light metering based on the average illumination in the entire scene, and thus result in areas of deep shadow or washed out light where you can't see any details. Another reason that this is actually a very good strategy for the visual system to employ is because high contrast edges, which is another way of saying lines, carry a lot of information relevant to the task of vision, as demonstrated by the simple contour drawing, where even though there's no shading or color or anything of that sort, you're able to very clearly discern that this is a picture, a cartoonish picture, but a picture of a person sitting in a chair. And the reason you're able to tell that is because lines separating different regions of the scene carry a lot of information about what is contained in that scene. So by reporting edges, the visual system is throwing away a lot of information that we don't need to understand the world and reporting information that is very useful in understanding the world. In closing, I'm sharing this quote of David Hubel, who did original recordings characterizing center-surround receptive fields, reflecting on a surprising fact about the way that our vision works, which is that the retina doesn't passively report what it sees, it actively transforms the data to encode only relevant features where relevancy is defined in context of the task of vision that we introduced several lectures ago. And here's what he says. Many people, including myself, still have trouble accepting the idea that the interior of a form does not itself excite cells in our brain, that our awareness of the interior as black or white depends only on the cell's sensitivity to the borders. The intellectual argument is that the perception of an evenly lit interior depends on the activation of cells having fields at the borders and on the absence of activation of cells whose fields are within the borders, since such activation would indicate that the interior is not evenly lit. So our perception of the interior as black, white, gray, or green has nothing to do with the cells whose fields are in the interior, hard as that may be to swallow. What happens at the borders is the only information you need to know. The interior is boring. Word, David Hubel.